Buckle up because we're diving into the heart of the cosmos today. You've probably heard that space is empty, right? Well, let me tell you it's not. Space is teeming with hidden forces and phenomena that are far from empty. First off, in any given point in space, you'll find gas, dust, charged particles from stars, starlight, cosmic rays, radiation from the Big Bang, gravity, and even electric and magnetic fields. But that's just scratching the surface. There are also two invisible heavyweights, dark matter and dark energy. And even if we could somehow remove all these things from a region in space, three things would still remain according to physicist Dr. Henning Gen's vacuum energy, the Higgs field, and spacetime curvature. So, what's vacuum energy? Imagine a sea of particles and antiparticles constantly popping in and out of existence. This isn't just a wild theory. It's a fundamental concept in physics. In fact, the laser in your DVD player relies on these vacuum fluctuations. These fluctuations can even be measured through the Casimir effect, where two uncharged metallic plates are attracted to each other in a vacuum. Crazy, right? Next up, the Higgs field. This invisible field permeates all of space and gives particles their mass. Remember the big news from 2012? That's when scientists at CERN's Large Hadron Collider found evidence of the Higgs boson, the particle associated with the Higgs field. This discovery was monumental because it confirmed how particles gain mass. Lastly, we have space-time curvature. Thanks to Einstein's general theory of relativity, we know that mass warps space itself, creating what we perceive as gravity. Think of the curved path of a satellite orbiting Earth. It's actually traveling in a straight line through curved space. Even in a completely mass-free area, space still has a shape and can be curved. So, even in the emptiest regions of space, you'll still find vacuum energy, the Higgs field, and space-time curvature. And in more typical vacuums, like outer space, you'll also encounter gas, dust, starlight, electric and magnetic fields, cosmic rays, neutrinos, and the elusive dark matter and dark energy. Despite all this, space does seem empty to us here on Earth, probably because we're used to being surrounded by a thick atmosphere. How much energy is there in empty space? Even the emptiest regions of space are teeming with energy, a phenomenon known as zero-point energy. This mysterious force arises from the constant fluctuations of quantum fields. Imagine a sea of particles and antiparticles popping in and out of existence, even in the seemingly empty vacuum. But what does this mean for our understanding of the universe? For starters, it challenges our perception of what empty really means. One such effect is the Casimir effect, where two uncharged metallic plates placed in a vacuum are attracted to each other due to these quantum fluctuations. Scientists are also exploring the potential uses of zero-point energy. Some theories suggest that vacuum energy could be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. Does the Earth get heavier with more people? At first glance, it might seem like adding billions of humans to the planet would increase its mass. But let's dig deeper. The Earth's mass is largely determined by the amount of matter it contains, including the atmosphere, oceans, and land masses. When people are born, they are made from the matter that already exists on Earth. Think about it. The food we eat, the water we drink, and the air we breathe are all recycled components of the planet's existing matter. So, in reality, the overall mass of the planet doesn't increase with the birth of more people. However, human activities can significantly redistribute this mass. For instance, mining operations extract minerals and metals from deep within the Earth and bring them to the surface. Construction projects then use these materials to build skyscrapers, roads, and bridges, altering the distribution of mass on the planet's crust. Similarly, waste production can end up creating large landfills, which also shifts mass from one place to another. In addition to these activities, human-induced changes like deforestation and urbanization can affect the Earth's surface and atmosphere. When forests are cleared for agriculture or urban development, the biomass is either burned or decomposed, releasing carbon into the atmosphere and changing the mass distribution between the biosphere and the atmosphere. But what about the overall mass of the Earth? Despite these redistributions, the total mass remains the same unless we consider extraterrestrial factors. For example, the Earth gains a small amount of mass each year from meteors and cosmic dust. On the flip side, we also lose a tiny amount of mass due to atmospheric particles escaping into space. Is energy lost in space? This question takes us to the heart of one of the most fundamental principles in physics, the conservation of energy. According to the first law of thermodynamics, energy cannot be created or destroyed. It can only change forms. But how does this principle hold up in the vast emptiness of space? To understand this, we need to consider the different forms of energy present in the cosmos. There's kinetic energy from moving objects like planets and stars, potential energy from gravitational forces, and even thermal energy from cosmic microwave background radiation. Then there's dark energy, a mysterious force driving the accelerated expansion of the universe. But what happens to energy as it traverses the seemingly infinite void of space? For instance, light from distant stars travels billions of light years to reach us. As it does so, its energy can be stretched by the expanding universe in a process known as redshift. This doesn't mean energy is lost. Rather, it's transformed into a different wavelength. Similarly, when particles collide in space, their kinetic energy can convert into different forms, such as radiation. This intricate dance of energy transfer and transformation ensures that the total energy in the universe remains constant, even if it changes form. How can you extract energy from any kind of light? Photovoltaic cells, commonly known as solar cells, are devices that convert sunlight directly into electricity. They are made from semiconductor materials, most notably silicon, which absorb photons and release electrons. These free electrons are then captured to produce an electric current, which can be used to power homes, businesses, and even spacecraft. But the story doesn't end there. Quantum dot solar cells represent an exciting frontier in light energy conversion. Quantum dots are tiny semiconductor particles, only a few nanometers in size, that have unique optical and electronic properties. By tuning the size of these dots, scientists can manipulate the wavelengths of light they absorb, potentially increasing the efficiency of solar cells beyond what is possible with traditional materials. Imagine buildings entirely covered with transparent solar cells, generating electricity while still allowing light to pass through. Or consider portable, flexible solar panels that could be rolled up and transported easily, providing power in remote areas or during emergencies. Future advancements in this field might include the development of multi-junction solar cells, which layer different materials to capture a broader spectrum of sunlight, or even the integration of solar cells with other energy harvesting technologies to create hybrid systems. In conclusion, the vast emptiness of space is a fascinating subject. Despite appearing empty, space is filled with energy and potential. From the mysterious dark energy to the intriguing concept of extracting energy from light, space holds many secrets yet to be uncovered. But what if we could harness this energy? Imagine future technologies that can tap into the boundless energy of space itself. Concepts like space-based solar power, where satellites equipped with massive solar panels collect sunlight unobstructed by Earth's atmosphere and beam it back to Earth as microwaves or lasers, are already being explored. Or consider the potential of capturing dark energy, the force accelerating the expansion of the universe. While this remains a theoretical possibility for now,